Okay, so in the previous lecture we were discussing about closed sets, right? Closure of a set and certain characterizations of closed sets. So let us just recall a few facts, and these properties were what we were discussing were pretty relevant to uh, these topics being discussed as in terms of metric spaces. Yeah, so we had defined that if you have a topological space x tau and you consider a subset of x, then we had defined the closure of A, right? The closure of A as the intersection of all the closed sets containing A, right? Containing A. And we had discussed a few facts that some element is in A closure if and only if every neighborhood of X intersects A, right? Every open neighborhood of X intersects A, right? This was one very important characterization we had. And then we had also discussed a few facts related to this, that so if you have a subspace topology, suppose Y is a subspace, then for an arbitrary set A in X, the closure of A in Y, let us just denote it like this. The closure of A in Y is the closure of A in X intersection Y. We had also discussed this. Yeah, so let this be A in Y, right? Clear? So yeah, this was a good discussion we had in the previous lecture. Okay. So typically, neighborhood of an element is it can be defined as a set B. So the neighborhood of some X is a set B such that there exists an open set U which contains X, that is containing X and contained in B, and contained in B. That is, X is contained in U and U is contained in B. So if I consider the concept of an open neighborhood, so open neighborhood basically open sets containing X. So that's the trivial discussion. Okay, clear? Okay. So today we want to discuss the concept of limit points, and then we will discuss a few concepts regarding a special type of topological space. Okay, so we start with the concept of a limit point. Limit point. Okay. So let X tau be a topological space. Be a topological space. Let A be a subset of X. Okay. Then an element small x in capital X is said to be the limit point of A if and only if every deleted neighborhood of X intersects A, or we can also term it as every open neighborhood, or we can precisely use the fact every neighborhood intersects A at a point other than X. That is, we can also say it in this form, that if B is a neighborhood of X, then B minus X, that is, we exclude the element X from B, this set intersects A. Okay, so that is the precise definition of a limit point. Clear? Obviously, we have used this definition of a limit point in terms of real analysis and in terms of metric spaces. That's identical. Okay. So, having defined the concept of limit points, one of the most obvious concern is how can we relate the closure of a certain limit point, as we used to do in case of the real analysis or in a metric space. So, we will do that itself. That is, let A be a subset of a topological space X tau. Let A dash, and that is it. This is indeed the notation used, be the collection of all limit points of A, and this set is called the derived set of A. It's called the derived set of A. Okay. Then that the closure of A is A union the derived set, right? And this is the exact relation we had previously also. Let us prove this. The proof is fairly simple. Why is it so? Because first thing, observe that if X is an element from A, then if X is an element from A, then for all neighborhoods U of X, you will have a non-empty intersection with A, right? Precisely, at least at the point X, right? At least at X, right? Because X is in U, because U is a neighborhood of X and X is in A as well. So that implies X is in A closure. So therefore A is contained in A closure, and that is also quite that was also indeed quite obvious by the definition of A closure, and yet we just wrote the statement. Now what happens if X is in A, the derived set of A? Then that implies for all neighborhood U of X, okay. So by the what is the definition? That every deleted neighborhood of X intersects A, right? So that means if for all neighborhoods U of X, U minus X intersection A is non-empty. Sorry, this is non-empty, right? But that exactly implies that U intersection A is also non-empty, right? As so this is quite trivial, because as if U minus X intersection A is at some point, or rather I should say it in this form. This is a wrong statement. I would obviously use. I should use this statement that if U, sorry, if U intersects A at some point other than X, then X is then including X in U will cause no change, right? Because if so, that means there are elements common in U and A which are not in X, which are not equal to X. Right? To be more precise, let me just convert this statement a little bit. I don't think that's quite trivial a statement. We change it just a little bit. I should say it in this form that as since U and A have common elements other than X, right? So since U and A has other elements, common elements which are other than X, so including X in U will cause no problem. That's the exact statement. So but that implies that X must be in the closure of A. So that implies the derived set of A is also contained in A closure. So A is contained in A closure. Derived set of A is it's contained in A closure. So that implies A union derived set of A must be contained in A closure, right? We just need to prove that A closure is contained in them. Therefore, to show that the closure of A is contained in A union the derived set of A. Okay. So let us first choose an element from A closure. So let X be an element from A closure. Now, if X is an element from A, then do we have anything to prove? Because if X is an element from A, then X is obviously in A union A dash. So that means A closure is an element. Sorry, it is contained in A union A dash, right? So therefore, let X be not in A. Okay. So if X is not in A, we need to show that X is in the derived set. Okay. So how do we do that? Suppose if X is not in A, but X is an element of A closure. Right? Since X is an element of A closure, that implies for all neighborhood U of X, U intersects A, right? But since X is not in A, so that implies if I just remove the element from U, because X is not in A, so if I remove the element from U, it will cause no problem, right? So this will also intersect, right? So, but that implies X must be in the derived set. So that means X must be inside A union A dash, and that means A bar is contained in A union A dash, right? Right. So therefore, A bar must be equal to A union A dash. Is this step clear? Since X is not in A, that means this U intersection A is happening at some point other than X. So just removing X from U will cause no problem. That's the only factor. Is it clear? So what is the immediate corollary of this? That is also one, the definition we are, again, we were quite accustomed with while studying closed sets. So what is the corollary of this? The corollary of this is immediate, right? That a subset A of a topological space is closed if and only if it contains all its limit points, right? It contains all its limit points. In other words, we can say that A is equal to A closure, right? Right. Yeah. So this was the basic categorization we used to have as a definition uh, in our study of real analysis or metric spaces. So I think this part should be pretty clear at this moment that topology is kind of a generalization of real analysis or the study of metric spaces. Indeed, the when we used to have the when we used to study metric spaces, we have studied the fact that every metric induces a topology. That is, if you have a metric space, then that eventually gives rise to a topological space. So topologies are basically generalized study of metric spaces. And obviously, when we used to study the real spaces, we used to study them as metric spaces only. We, we would not have declared that when we used to study real analysis. But whatever work we did using the elements of using the real elements, they were concerned work with respect to the standard metric on R. Okay. So now let us discuss a special type of a topological space which is of extreme use. Okay. Let me not name it at this moment. We will name it later. First, study a few important observations. That is, consider R with respect to its standard topology. That is the topology generated by the open intervals. Okay. Now, can we write this singleton set A? So, for all A in R, can we write the singleton set A as minus infinity to A, or let us just simply write it as or my question is in this form. Let's say my question is in this form that if I choose an element A from R, that is if A belongs to R is closed. And that is my question. Isn't it obvious? Because if you consider the complement of this, then this is nothing but this set, right? Minus infinity to A union A to infinity, right? right? And this is an open set, this is an open set. So this is an open set, right? That implies complement is open in R, right? But that immediately implies that this is closed. Right? And since A is arbitrarily chosen, so this happens for all A in R. Right? Therefore, in R, finite point sets, because if the singleton set is closed, we know that finite union of closed sets is closed. So finite union of singleton sets is closed, and finite union of a singleton set is a finite set. So finite point sets are closed. Indeed, singleton sets, right, are closed. This happens in R2 as well analogously. Similarly, for the standard topology over R2, clear? Where we consider the open intervals as open balls, where in R2 the open intervals are the open balls. Okay, the standard metric, that is the standard metric, which is, d of xy. This is given as it's x1 minus y1 whole square plus x2 minus y2 whole square, the root of it, where x is component wise x1 x2, y is component wise y. Yeah, so we can consider this topology, the Euclidean metric. I think we also name them as D2, right? Acha, one second. Okay. So we find that over R and R2 we have one point sets closed, right? So now my question is that is this property general? Okay, is this property general? That is, if I consider any arbitrary topological space, then is this property general? So one obvious answer is no, right? So let us just consider an example. Suppose you consider this topology. Let's say. So you have a, let's say you have a 3-point set. You have the set A, B, C. So consider this topology on X. So it's empty set. Then the set A, B, B, C, B, and X. Okay, consider this set. Now B is in tau. Okay, B is in tau. So B is basically open, right? Well, let us not discuss this as B as element of tau. We can say what is the complement of B? That is X minus B. So it's basically AC, right? But AC is not in tau, right? So that implies the singleton set B is not open. Sorry, is not closed. So single point sets are not closed in general for a topological space, right? That is, so one immediate observation is that the topological properties on R, to be very specific, or R2 are not general in nature, right? Now, there is something very unique about the standard topology on R and R2. We will be more specific about talking about the standard topology on R, but we also include in the literal sense R2 because that's quite similar to R. For example, what happens in R is that, recall in R, every sequence, if convergent, it converges to a unique limit, right? It converges to a unique limit. But does this happen for any arbitrary topological space or any arbitrary metric space? Okay, so See, consider this example only. What is the definition of convergence of a sequence in terms of a topological space? So let us just define that first. Definition. Let X tau be a topological space. A sequence Xn. So obviously this sequence is a function from n to x, right? So sequence Xn in X is said to converge to some small x in capital X if, or I should say, provided that, sorry, if for all neighborhood u of x there exists some n naught in n such that whenever n is greater than or equal to n naught, xn is in u. Right? So that's quite relevant to the definition we had in terms of in the real line, right? In real line, what did we used to have? We said that for all epsilon greater than 0, there exists some n naught in n such that n greater than or equal to n naught implies xn is in this interval, right? So it's in x minus epsilon, x plus epsilon. But this for all epsilon greater than 0 is exactly all open neighborhoods of x, right? That is what we have here. So every neighborhood of so xn is inside every neighborhood of x after a certain point n naught, right? Other way of describing is that every neighborhood of x contains a tail of xn, right? So a certain part of the sequence after a certain natural number n naught is termed as the tail of the sequence. Okay. Now that's the pretty intuitive definition of a convergent sequence in a topological space. So my question is that whether every convergent sequence has a unique point of convergence in a topological space or not. So we considered the topology we just defined on a 3-point set. So it was phi, AB, BC, and I guess we had B and X. Observe that if we consider the constant sequence Xn is equals to B, right? Then Xn is a sequence in X for obvious reasons. But Xn converges to B, A and C at the same time, right? Right? Because if I consider the open neighborhood of B, then Xn is in the open neighborhood of B, because obvious. So what are the open neighborhoods of B, A and C? So they are A, B, B, C and B on it, right? So Xn will converge to B because it goes inside this open neighborhood of B. It will converge to A because it goes inside the open neighborhood of A. It goes to C because it goes in the open neighborhood of C. But that's for obvious reasons. So therefore we have 3 distinct points of convergence of Xn. Right? So therefore it also gives us the fact that there is something very unique in the topology of R and R2. Right? So specifically talking that we are more concerned about those topologies in which the point of convergence of a sequence is unique. Right? Because precisely those topologies in which the point of convergence of a sequence is not unique, they seldom appear in the areas of mathematics. So that's not of much importance. Clear? So what we do is that we consider topology and we try to remove these fallacies that it has distinct points of convergence, and you know and similar things, such that we can frame it to be very similar to the topology of R or R2. And here comes the one of the most important topology, which is the Hausdorff topology, or the Hausdorff spaces. Okay, the definition: a topological space X is called a Hausdorff. One second. Yes, so topology X is called a Hausdorff space if for each pair x, y in X, such that X is not equal to Y, there exist disjoint open sets. So since we are considering topological space, the term of open sets is well defined. So there is disjoint open sets U and V, such that X is in U and Y is in V. So basically what is happening here, just a diagrammatic representation. So let's say, suppose this is the topological space X. You consider a point X, you consider a point Y, they are distinct. So there exists disjoint open sets. So suppose this is the open set U and this is the open set V. Open set, yeah. So this is the open set U and this is the open set V. I guess it's clear now, right? This is what actually happens in a Hausdorff space. Clear? Clear? So theorem, and from this theorem we will be able to understand why we have introduced such a concept. Every finite point set in a Hausdorff space is closed. Okay. Why is it so? Oh, sorry. I should say, how is it relevant? Because we have just noticed that every finite point set in the real field with respect to the standard topology is closed, as well as in R2. So therefore, that's a Hausdorff space, to be very specific. Right. So Hausdorff space is kind of a collection of all those topologies which are similar in structure to the standard topology of R and R. So every finite point set in a Hausdorff space is closed. Let's just prove it. It's very simple. What we do is that let x0 be an element of X and X be an element from X minus the singleton set x0. So that is basically X is not equal to x0. Okay, but since X is not equal to x0 and capital X is a Hausdorff space, right? So since X is a Hausdorff space, there exists open sets U and V, such that X is in say V, x0 is in U, and U intersection V is empty. Okay, clear? So now V is a neighborhood of X and X is not equal to x0, right? So V intersection x0 must be empty, right? Since if V intersection x0 is non-empty, that means x0 will be in V, but that would mean V intersection U is non-empty because x0 is always in U. So that's a contradiction. Therefore, a contradiction, right? So we should have this. But if V intersection x naught is empty and V is a neighborhood of x is a point distinct from x naught. So, but since V intersection x naught is empty, so that would imply x is not a closure point of x naught. Right? That is, x is not containing x naught. And since x was arbitrarily chosen, so any element x not equal to x naught cannot be in the closure of x naught, right? So that typically means that the closure of x naught is exactly equal to the singleton set x naught. And that means the singleton set x naught is closed, right? So if a singleton set x is closed, that is, if a one point set is closed, then every finite point set is closed, right? But that necessarily means every finite point set is closed. As finite point sets, right, are finite unions of singleton sets. And we had this, right, that finite union of closed sets is closed. Right? Right. Okay. In fact, this theorem is kind of a weaker axiom than the Hausdorff property, because there exist other topological spaces in which the finite point sets are closed, but it doesn't obey the definition of a Hausdorff space. That is, there exist topological spaces with one point sets closed but not being Hausdorff spaces. That is, for every distinct elements x and y, there does not exist disjoint open sets each containing x and y respectively, but not being Hausdorff spaces. An example is the finite complement topology. We know that in a finite complement topology, by its exact definition, every finite point set is closed, right? Every finite point set is closed, but it is not Hausdorff. It is not Hausdorff. You can verify it as an exercise. This part is trivial. Just check this. Okay. Such spaces, that is, spaces in which finite point sets are closed, simply we have this axiom that finite point sets are closed or singleton sets are closed simply. Such spaces are called T1 spaces. And this axiom of finite point sets being closed is called the T1 axiom. So Hausdorff space is necessarily a T1 space, but the converse is not true. Clear? Okay. The next property is again very important, which is theorem that if X is a Hausdorff space, then every convergence sequence in X has a unique point of convergence. And why is it so? So let xn be a sequence in X, be a convergent sequence in X, such that xn converges to X and xn converges to Y with X not equal to Y. So we assume that the given statement is not true and we will reach some point of contradiction. Right? Now since X is not equal to Y, therefore there exist disjoint open sets. Since we are working in a Hausdorff space, so there exist disjoint open sets U and V such that X is in U and Y is in V. But since the sequence xn converges to X, therefore U contains a tail of the sequence xn, and similarly V contains a tail of xn as well, right? But that implies U intersection V is empty, is non-empty. But that's a contradiction, right? But that's a contradiction because we had U and V to be disjoint open sets, but that is a contradiction. Right? Right? So therefore, they must so this contradiction comes from the initial assumption that X is not equal to Y. Therefore, X must be equal to Y. That is, we have a unique point of convergence. Right? And this is in relevance to what we have inside the topology, standard topology of R and R. Right? So, also a term to be specified here, that if a sequence xn converges to a point X, then X is said to be the limit of X. Okay, and is unique in terms of in a Hausdorff space, right? Clear? Okay. So the last important property of Hausdorff spaces, let's discuss it. Theorem. Let X be a space satisfying. So we prove this for the T1 axiom, satisfying the T1 axiom. So if X is a Hausdorff space, then it necessarily satisfies the T1 axiom. So this theorem is true for Hausdorff spaces as well, right? Right. So, theorem. Let X be a T1 space, that is finite point sets closed in X. Let A be a subset of X. Then X is a limit point of A if and only if every neighborhood of X contains infinitely many points of Clear? We knew that X is a limit point of A if and only if every deleted neighborhood of X intersects A, but here we have that every neighborhood of X should intersect A at infinitely many points. So that is, so every neighborhood of X containing infinitely many points of A, that indeed means that every neighborhood of A every neighborhood of X intersects A at infinitely many points. Right. Now one part of this statement is trivially true, right? That is, if U is a neighborhood of X, and u intersection A is infinite, then obviously deleting the element, deleting the element x from the neighborhood u won't cause any problem, right? So that implies u intersection x, u minus x intersection A is also non-empty, right? So that implies x is an element from, so x is a limit point of x, right? That is, x is a limit point of. So we need to show that if x is a limit point of A, then the intersection happens at infinitely many points. Okay. So conversely, suppose x is a limit point of A. We assume that every neighborhood of x intersects A at only finitely many points. At only finitely many points. Okay. Or we will reach some point of contradiction and then we are good to go, right? So let u be a neighborhood of x. I should be precise of that some neighborhood of x, right? That a neighborhood of, yeah, so that a neighborhood of x intersects A at only finitely many points. Let the neighborhood be u. What should be the negative of this statement? That every neighborhood of x intersects A at infinitely many points. So then let the neighborhood be u. Then u intersection, then u intersection A is finite, right? So if u intersection A is finite and x is a limit point of A, since x is a limit point of A, so this intersection except the element x is also finite, because if u intersection A is finite, x is an element of u. So if I remove x from the complete intersection, then it's still finite, right? Then, so now we remove x from A, right? Okay, so that will be a good procedure. So u intersection A minus x is finite. So not using the word finite, let me give the mathematical form of it being finite. So we consider this to be the set of elements x1, x2 till xn. Okay. Now consider the set. See, typically speaking, x is a limit point if u minus x intersection A is non-empty. But that is same as writing u intersection A minus x is non-empty, right? But equivalent statements, because you just need to remove x from this intersection. X is surely in u, right? So if x is not in A, that makes no difference. But if x is in A, so if you remove x from A or you remove x from u, it actually gives the same result, right? So we consider the set x minus these elements, so x1, x2 till x, right? Therefore, sorry, let me be precise. Now x is a T1 space, right? That was our assumption. One sec, there's a certain lag. Oh, yeah. So x is T1 space. So that means every finite point set in X is closed. So that necessarily means that this set, because this is a finite point set, that means X minus X1, X2 till Xm is open. right? But small x is an element of x minus this set, because small x is not an element from one of these elements x1 x2, because we have considered x1 x2 till xm to be the elements at intersection of u intersection a minus x, right? So that means this forms an a neighborhood of x, right? Therefore this is a neighborhood of x. Therefore indeed u intersection x minus, because x is in both, so x is also in u because u is considered to be a neighborhood of x, and x is also in this set, so this also becomes a neighborhood of x. So x, so and now, so they are both open, right? So intersection of open sets is open set, and x is in both of these sets. So u intersection capital X minus x1 x2 till xm is an open set containing x, so it's a neighborhood of small x. But u intersection x minus x1 x2 till xm, it does not intersect a minus x, right? But x was a limit point, right? X was assumed to be a limit point, so every neighborhood of x should intersect a minus singleton sets. So therefore a contradiction, right? Therefore a contradiction to the fact x is a limit point of a, right? And where does this contradiction arise from? So it arises from the hypothesis that the intersection happens at finitely many points. So therefore u intersects x at infinitely many points. Okay, clear? So yeah, so we are done for today. I'll try to bring some important concepts related to topology if I get enough time to do so. Okay. So our main concern in this channel is to study algebra. The main concern of this channel is to study algebra, but I'll keep on trying to bring certain lectures of analysis or analytical topics as well. So meet you guys in the next lecture.